Good morning and welcome to this next lecture on sound and structural vibration. So we were looking at far field, or we were going to look at far field acoustic directivity, and I said the integral we were interested in is I omega f by twice pi b integral minus infinity to infinity e to the power I k x minus gamma y dk by k fourth minus kp fourth gamma minus mu kp fourth. Okay. So we will consider r tending to infinity. Okay. And what is r? R is equal to square root of x square plus y square, where x is r cos theta and y is r sin theta. Okay. Now phi of x comma y is rewritten as integral minus infinity to infinity f of k e to the power of r I k cos theta minus gamma sin theta dk. Okay, where f of k is I omega f by twice pi b 1 over k fourth minus kp fourth gamma minus mu kp fourth. Okay. So this is the integral. Now we have seen that in the stationary phase, okay, method of stationary phase, we have this function e to the power a certain function, okay, of the form I x h of omega last time we saw. Okay. So that function for us here, okay, is h of k, which is given by k cos theta plus square root of k0 square minus k square sin theta. Okay. So let's see. So my phi of x comma y written in the stationary phase nomenclature minus infinity to infinity f of k as given before e to the power of I r h of k dk, where let me just repeat, h of k is equal to k cos theta plus square root of k0 square minus k square sin theta. Okay. So now we need to find a stationary phase point, that means a point where h dash of k is equal to 0. we need to find that k value. We'll call it k hat. K equal to k hat value, where h dash of k hat is 0. Okay, so if h of k is this, then h dash of k is equal to cos theta, okay, plus 1 by 2 square root of k0 square minus k square into minus 2k into sine theta. Okay, that should be equal to 0. Okay, so that means what? Means my k hat sine theta must be equal to square root of k0 square minus k hat square into cos theta. Okay, square, we square both sides. We square both sides. If we square both sides, we get k hat square sine square theta is equal to k0 square cos square theta minus k hat square cos square theta. So if we combine this and this, we get k hat square is equal to k0 square cos square theta, or k hat is equal to k0 cos theta. That means k hat is within 0 and k0. Okay, so this has two roots, one positive going, one negative going. We are considering the positive going root. Okay, so what is my gamma hat now, or gamma at k hat now? Is equal to minus I square root of, okay, k0 square minus k0 square cos square theta, which is equal to minus I k0 sine theta. Okay, now the second derivative, of h of k, okay, of h of k. Okay, so let's see, h dash k gave me cos theta minus sine theta k by square root of k0 square minus k square. Okay, so this was h dash of k, and h double dash of k gives me 0 here. Then let's keep a minus outside. Then I get a sine theta square root of k0 square minus k square minus 1 by 2 square root of k0 square minus k square minus 2k, okay, into k sine theta divided by the square, which is k0 square minus k square. Okay, now already I know that my k hat is k0 cos theta, Okay, so I get minus, so I have to evaluate this at k hat. So I get minus sine theta, okay, into k0 sine theta, okay, then plus k0 square cos square theta sine theta by k0 sine theta, okay, divided by k0 square sine square theta. Okay, so this gives me, I lose this one here, I lose a k0 here, so I get minus k0 by k0 square sine square theta, which is equal to minus 1 by k0 sine square theta. Okay, the formula, I suppose I didn't write the formula this time. Okay, so the formula, let's see. If we had y of x given by integral minus infinity to infinity f of k e to the power of I x h of k dk, then the answer is y of x is equal to twice pi by x h double dash at the optimum phase value k hat e to the power of I x h k hat plus or minus pi by 4 as x tends to infinity. Okay, so in this case here, my h double dash of k hat turned out to be minus 1 by k0 sine square theta. Okay, so h double dash of k hat to the power half is given by I by k0 root sine theta. Okay, so what I have is, if I plug my expression in, my y at r, let's say, becomes equal to twice pi by r whole to the power half, and h double dash k square root becomes I square root of k0 sine theta, then e to the power I r, okay, h dash at k, okay, is equal to k0 minus pi by 4, okay, into f at k0 cos theta. Okay, so if we rewrite this now, my f of k was equal to I omega f by twice pi b k fourth minus kp fourth into gamma minus mu kp fourth. Okay, so f at k equal to k0 cos theta becomes equal to I omega f by twice pi b into k0 fourth into cos 4 theta minus kp fourth square root of k0 square cos square theta minus k0 square minus mu kp fourth. Okay, so if we examine this part here, we will get equal to I omega f by twice pi b 1 over minus I k0 sin theta into k0 fourth cos 4 theta minus kp fourth minus mu kp fourth. Okay, so if this is plugged back in here, what is the total expression? My y at r going to be equal to or let me write it as yeah, let me write right now temporarily I omega f by twice pi b twice pi k0 over r, okay, to the power half sin theta e to the power I k0 r minus pi by 4 divided by minus I k0 sin theta k0 fourth cos 4 theta minus kp fourth minus mu kp fourth. Okay, this is actually my phi of x comma y. Okay, so from here if we have to make a pressure out of it, then just multiply by I omega rho times phi. I omega rho times phi. So if we do that, my pressure is equal to twice pi k0 by r to the power half. Okay, rho omega square f by twice pi b e to the power I k0 r minus pi by 4 sin theta divided by k0 fourth cos 4 theta minus kp fourth into I k0 sin theta plus mu kp fourth. We'll further write this as equal to twice pi k0 by r to the power of half rho omega square f by twice I pi b kp fourth k0, okay, e to the power of I k0 r minus pi by 4 sin theta by m fourth cos 4 theta minus 1 sin theta minus I alpha. Okay, which we'll write as equal to twice pi k0 by r to the power half rho omega square f by twice pi b kp fourth k0 okay into I e to the power of I k0 r minus pi by 4 sin theta by 1 minus m4 cos 4 theta sin theta plus I alpha. Okay, now we write P as equal to f by twice pi b into twice pi k0 over r half rho omega square e to the power I k0 r plus pi by 4 by kp fourth k0 into d m theta alpha, okay, where d m theta alpha is the directivity function, okay, given by d m theta alpha is equal to sin theta by 1 minus m to the power 4 cos 4 theta sin theta plus I alpha. Okay. So alpha is also a fluid loading parameter. Which turns out to be epsilon over m squared. Okay, so in that sense alpha carries frequency in it. Okay, so now we will examine this directivity function to discuss the acoustic, okay, coupled acoustic directivity. We should note that we are talking k hat is equal to k0 cos theta, which means we are above coincidence. Okay, so below coincidence there is no sound. Okay, there is no wave number that can generate sound. We are talking above coincidence. Now if you look at this factor which is called directivity, for alpha much less than 1, the directivity is a perturbation to alpha equal to 0. Okay, alpha much less than 1 means epsilon over m square much less than 1, which implies m much greater than epsilon to the power half, which we have seen in this range the fluid loading or inertial loading is insignificant. Okay, that means uncoupled analysis is good enough. Uncoupled analysis is good enough. Now when alpha is 0, we get the directivity d given by 1 over 1 minus m to the power 4 cos 4 theta, and m is greater than 1, and therefore there is an angle cos theta m 1 over m kp by k 0, where d tends to infinity. Okay, this angle theta m is called the Mach angle. The Mach angle. Now at the Mach angle, if now we look at the d factor, okay, with fluid loading, then it becomes finite. Okay, so there is a drastic change. So at Mach angle, fluid loading is significant. Which means uncoupled analysis is not good enough, not adequate. You have to do the coupled analysis. Okay. Next, for theta very small, that means close to grazing, okay, you can see that d is equal to theta over 1 minus m to the power 4 theta plus I alpha. Okay, so d tends to 0 as theta tends to 0 regardless of alpha. Okay, whereas in the uncoupled analysis, d is equal to 1 over 1 minus m to the power 4th a constant. Okay, at theta equal to 0, which means what? Which means at theta equal to 0, at grazing incidence, again fluid loading becomes significant. Okay, so that is as far as coupled fluid directivity. Okay, now let me just summarize this here, summarize the whole situation. In vibrations, okay, in the vibration part, below m equal to 1, we get two roots. Okay, one is a subsonic root, one a coupled, one a complex root, neither produces sound. Then above coincidence, we have one subsonic root. So let's say this subsonic root is near Kp. We get one subsonic root, okay, that is near K0. Then we get again that one complex root, then we get one supersonic root. Which is near Kp, okay, that is called the leaky pole, that is responsible for sound, okay. Other than that, from the branch line integrals, the B1 and B2 branch line integrals, we get a vibration contribution which has this as the dominant propagator, and it decays as x to the power minus 3 by 2. Okay, and the sound part we have seen just now, already discussed. Okay, so with this I close this topic of this classical problem. So there's a lot of new and deep material in it. I hope it's useful. Thank you.